In this module, we will discuss a special class of mesoscopic electrical amplifiers, namely charge amplifiers or charge sensors. And we will focus on the charge sensing techniques in quantum dots. And for this particular lecture, we will discuss the quantum point contact charge sensors and its application in sensing charges in quantum dots. So just before we discuss the charge sensing technique, let us briefly look at what is the need of a charge sensor. What we have here is a Coulomb diamond data, Coulomb diamond plot taken for a semiconductor gated quantum dot. And as we have discussed in the previous module, one of the previous modules, as you go from the right to left in this plot, okay, you are reducing the gate voltage and you are reducing the number of electrons as you successfully go from one diamond to the next Coulomb diamond. And the color scale which is representing the current to the device is given here. And we know the size of the diamond directly gives you the size of the dot via the charging energy. And you can see that the size of the diamond increases, which says the charging energy is increasing as you go from right to left, or the dot size is decreasing. Just to represent it diagrammatically, say when you start, the dot is comparatively larger in size, and towards the left, as you reduce the gate voltage, you will increase the Coulomb diamond or reduce the dot size, reduce the number of electrons, and eventually dot will be really small, and the assumption is you will empty the dot. So now the question is, can we assume that this region here is void of electrons in the dot? Or do we have an empty dot here? So when you say empty dot, the Coulomb diamond will open up but it doesn't close back. Okay. If you look carefully, here you can see that the last diamond is like this, but I don't see a lot of signature of its closing back. Okay. So the question is, can I assume that this is 0 electron, this is 1 electron, 2, 3, 4, 5, and so on? But that's not really clear, because you are actually doing a current measurement, and every current preamplifier which you use to measure the current to the device has certain sensitivity limits or lower limit or lower bound of sensitivity. Okay. So usually anything which is less than a few femtoamps is almost immeasurable. As you can see from this plot, the current level is gradually reducing, because when you started, you have a large dot with lower voltages on all the gates, and the tunnel barriers are relatively thinner. The tunnel barrier here represented by this barrier in these gaps, and you have a lot of electrons. And when you made the gates negative, you actually made the dot smaller, and you can see that now the tunnel barriers are thicker, right? Because you have a lot more negative voltage. To make the dot smaller, you have to basically increase the negative voltage. So the field is going to creep inside more and more, and you have more or less a much broader tunnel barrier. So you have a very thin tunnel barrier here, but whereas you have a thick tunnel barrier here when you reach the few electron regime or close to the dot being empty. Now the current through this device, that is I, is basically a function of the tunnel rate. E is the charge, minus E is the electronic charge, and gamma is the tunnel rate through this tunnel barrier. Now the tunnel rate through this barrier here will be high because the barrier is thinner. But here the tunnel rate through this barrier can be very, very low, very, very small, so that this current I is almost immeasurable. So there is no guarantee that the dot is empty in this regime. The current is low doesn't mean that, or you cannot measure the current, it doesn't mean that the dot is empty. The tunnel rate could be very, very low, so that the current is beyond what you can measure, is below or much, much lower than what you can measure with your current preamplifier. So what we have is a very low tunnel rate. The measuring the current is not a good choice in the few electron regime, and that you will see very soon. But what you can do is, you can actually sense the charge. You can see whether there is an extra electron there or not. You can sense the motion of the charge. Okay, so if you have some kind of device where you can sense the charge rather than sensing the current senses the tunnel rate, whereas the charge sensor, which actually is going to sense the charge, not the rate, whether there is a transition or not, that the overall electron number is changing or not. That's what the charge sensor is going to sense. So what you really need is actually charge sensor, not a current sensor in this, specifically in this case. Okay, and that is the topic that we are going to discuss for this and the next 2 lectures. So let us also get some idea on the sensitivity of the IV measurements. The IV measurements are the conventional transport measurements. Okay. So what I have here is a representative plot of electron transmission rate. Okay, and the current on the y-axis, and of course it is actually going to be a straight line. And when the electron transmission rate is less than a few tens of kilohertz, your current is going to reach in the femtoampere range, whereas the typical current preamplifier noise floor falls in that range. Okay, around maybe 5 to 10 femtoampere range is what you are going to get for a typical highly sensitive current preamplifier. So whenever the current is in this range, that electron transmission rate is in this range, current is in this range, you cannot really rely on a current sensing, or you cannot measure the current through the device. irrespective of whether it's a quantum dot or nanowire or whatever the device you have. But if the transfer rate of electrons through system is in this regime, then current measurement is not an option to characterize the device. For example, many low-dimensional systems such as nanowires, quantum dots, long organic conducting polymers, DNA, many of these actually falls in this regime where electrical transport measurement using conventional IV characterization is almost impossible. Whereas here, the transmission rate for electrons are higher and you can measure current through the system with the conventional current voltage characterization. One example we just discussed, the transport of electrons through the quantum dot, which is represented here. So in the few electron regime, these tunnel barriers can become really thick and this transfer rate of electrons can be very low and can easily fall in this regime, which we will see in one of the coming slides. Okay. So, in a nutshell, the current is proportional to tunnel rate, and tunnel rate for many of these low-dimensional systems that we encounter are below a few megahertz, can be in kilohertz, where conventional current measurement is not possible. And one can sense a charge movement. That is probably the solution to it. Current is basically charge in time, so you can sense the charge movement and you can back calculate what is the current through it. But even for quantum dots, what is more important is to know whether there is an electron or not, or what is the charge state of the dot, which is more important than measuring the current. So measuring the charge is actually more straightforward for a quantum dot rather than measuring the current through the device. So that is the take-home message here. So when we say charge sensing, what we are really sensing is the electric field due to the charge. Okay, so you have a change in the charge configuration, and what you are going to sense is a change in the electric field due to that charge. But what we are interested is, especially in quantum dot research or qubit research, is the change in one electron in the system. Not like many electrons, one electron, but what changes that you are going to observe? How can you sense when the dot goes from 0 electron to 1 electron or 1 electron to 2 electron? Okay, which is pretty challenging. So let us look at the classical charge sensing amplifiers that we encounter. They are basically field effect devices with this configuration, which we have discussed in the introductory session. So the current through this system is a function of the gate voltage. So to change the gate voltage, what you are doing is you are actually changing the gate charge. So whenever you change a small amount of gate charge, that is going to be reflected as a change in the current through system. You can apply small wiggle on the gate, electric field oscillation, electric voltage oscillation, which is going to change the charge, which is going to change the electric field felt by the channel here, the electric field filled by channel here, and that is going to show up as a change in the current through system, and that is the amplification that you are getting. So you have amplified some charge oscillation delta Q in terms of the current or conductance of the system. And these are large systems obeying classical laws of physics, and bandwidth is kind of limited. You can get like hundreds of milliseconds is what you're going to sense, what you could sense generally and the typical sensitivity is 0.1 electron per root hertz. Okay, what that means is 1 electron you can sense in 100 millisecond time scale. Usually, the unit for sensitivity always is specified in this fashion, electron per root hertz. Okay, what that means is, in this specific case, you can sense one electron or movement of one electron if a time of 100 milliseconds is given. So you need that much long time to sense one electron. But remember, many of this charge transfer process happens in nanoscale to nanoseconds time scale to picoseconds or microsecond. That is how the charge dynamics happen in solids. So this is not a viable option to sense charge motion in mesoscopic device. First of all, these are much larger in geometry because they have large capacitance and slower response. And this transport is classical, so subject to a lot of classical noise. They actually can disturb the transport in the system that you are trying to probe. So this is not a good option to do charge sensing in mesoscopic systems such as quantum dots. Now, what you have in hand to do these measurements is another mesoscopic but field effect device. Okay, that's a quantum point contact. What we have learned is the conductance of the quantum point contact exhibit this step-like behavior as a function of the gate voltage. And between the plateaus in the conductance, the current through the device changes very sharply. What that means is the device is extremely sensitive to local fluctuations in the electric field if you were around any of these plateaus, between the plateaus, around these steep regions. So in this configuration, what we have is a quantum dot, gate-defined quantum dot, and this gate on the side and this one on the other side. When you energize these gates, you can define a quantum point contact or a channel, thin channel on both sides. This side also you can define a thin channel. This also another quantum point contact where the current IQPC is a strong function or is really sensitive to the local variations in the electric field. So the idea is any change in the charge configuration in the nearby quantum dot, which is represented by the circle here, any change in the charge configuration or electron occupancy can change the current or conductance of the device. And you can measure the conductance of the QPC, and from the fluctuations in the conductance, you can sense the fluctuation in the electron configuration or occupation of the nearby quantum dot. That is the point here. So in this specific case, what I have is a Coulomb blockade oscillation being sensed by the charge sensor, in this case the quantum point contact. So what we are doing here is you are changing the gate voltage Vm. Vm is the voltage on this middle gate, that is Vm. And when you sweep this gate to negative direction, you are removing one electron out of the dot. So this event of the electron tunneling out of the dot is going to put a small change in the conductance of the QPC. So here this curve shows the QPC conductance, and the small bump in the data here is due to the electron tunneling out of the dot. So that is a signature that you are going to get in the QPC conductance when electron goes out of the dot. So right side of this bump, you have the electron inside the dot. And the left side of this bump, you have the electron outside the dot. Okay. So remember, in this specific case, the dot is in the one electron regime, and the tunnel barriers are really, really thick, broad, so that you cannot measure any direct current through it. So the only way to know whether the electron has gone out or it is inside is by using a charge sensor. Current measurement is not reliable in that regime. And this is just to explain that this is the effect that you are going to see when an electron moves out of the dot or into the dot. And this trace here is a conductance of the QPC, or the derivative of this trace. Okay, so you will see peaks similar to Coulomb blockade peaks, but these are the conductance changes in the QPC, not the Coulomb blockade peaks, but this stands for Coulomb blockade oscillations, because in this range, Coulomb blockade oscillation cannot be measured directly by measuring the current through the dot. Okay, so that is the technology, or that is a technique to sense the charge in, or charge movement in gated quantum dots. These are a couple of representative experiments where the quantum point contact has been used to sense the charge in a single quantum dot, charging and discharging events in single quantum dots. So what we have here in this experiment, this is the first experiment on detecting charge motion in a single quantum dot using quantum point contact. What we have here is a gated quantum dot and a quantum point contact channel. And the Coulomb blockade oscillations in the quantum dot are shown here. These are the Coulomb blockade oscillations. And the corresponding conductance change, or the resistance change in the detector circuit, which is the quantum point contact, is shown here. So as you can see, whenever the electron number changes through the dot, that is felt by the QPC, and it displays a bump. That's what we are seeing here. And here there's a plot of the change in the dot potential extracted from the resistance change in the detector, the details of which we will not discuss now. So the point here is the Coulomb blockade oscillations here are felt by the current through the detector circuit, which is the quantum point contact. Okay, and this is the first report on the use of quantum point contact to sense charge motion in single quantum dot. This is another example where you have a quantum point contact which is defined by a local oxidation technique on gallium arsenide, aluminum gallium arsenide heterostructure. And you have quantum dot and you have a quantum point contact channel. And the Coulomb blockade oscillations of the quantum dot is shown here. And as we have discussed, you can see the height of the Coulomb blockade oscillation is actually decreasing as you make the gate voltage more negative. But the charging and discharging event sensed by the quantum point contact, which is now shown as the bump in the conductance of the quantum point contact, is not affected by the change in the gate voltage because it is not sensing the tunnel rate, it's actually just sensing the charge, the presence or absence of the charge, or change in the charge configuration or charging and discharging events. So that is not affected by the negative gate voltage, but the current through the quantum point contact, you can see that is greatly affected by the tunnel rate, and that it goes down drastically as the gate voltage is made more negative. You can see this peak height that the Coulomb blockade oscillations goes down drastically as the gate voltage is made negative. This is already in the picoampere scale. Okay, this is like fraction of a femtoampere now already. And but the signal from the quantum point contact which matches with these transition are unaffected by the tunnel rate, decrease in the tunnel rate, and that is the main advantage of using a charge sensor in place of a current sensor. Okay. Now, what we have here is a situation where no measurable current flows through it, but you can still see there are plenty of electrons in the dot. Okay, this is telling you that measuring the current is not a reliable way. You have to measure the charge to see whether the dot, to characterize the dot, to see whether the dot is empty or how many electrons are there in the dot. This is really, really crucial, especially when you define the quantum bits using the electron states in the quantum dot. So this is a SEM image, scanning electron microscope image of the gate structure, and when you energize this gates, you are going to get a quantum dot in this region. Okay, and there is a quantum point contact channel here. Okay, and these are the Coulomb diamonds, and these are the Coulomb blockade oscillations to the dot. The blue traces are the Coulomb blockade oscillations, and the red traces are the conductance through the quantum point contact channel, the conductance stage. Now, as you can see, the height of the blue trace goes down drastically, and you cannot see any sign of the Coulomb blockade oscillation beyond this point. Okay, so naturally, one would be tempted to assume that all the electrons have tunneled out, there are no electrons moving through, right? That is the natural tendency. But the sensor signal, the signal from the quantum point contact, is telling you there are still a lot of electrons going through the quantum dot. That means the quantum dot is not empty. And each of these peaks matches exactly with the peak position here, but beyond which you cannot sense the electron motion by sensing the current, but you can still sense the charge motion through the quantum dot from the conductance changes in the quantum point contact channel. So you can actually measure the current when just by counting the number of electrons, which we will discuss in a minute. Okay, using the charge sensor, where any of the available techniques to measure the current by current sensing fails. So in this region, though we are tempted to believe that there are no electrons, but as per this data, there are plenty of electrons still in the dot, and dot is not at all empty. And we are not in the one electron regime yet. Okay. That is another example where charge sensor is crucial to characterize the dot. Now, here are a couple of examples where the charge sensor is used for characterizing the double quantum dot. When we discussed double quantum dot, we went through the charge stability diagram, which is the current through the dot or conductance of the dot as a function of two gate voltages. And you will get this honeycomb shaped pattern, and that is the signature of the formation of a double quantum dot. And from the geometry of these diamonds, you can extract a lot of information regarding the geometry of the quantum dot. Okay. Here, this one example where you are using a quantum point contact, which is one of these channels. There are two quantum point contacts in this geometry in this device, and there are two quantum dots. Okay, this one quantum dot here, one quantum dot here, and the current through the quantum dot goes in this direction. The dot 1, dot 2, and then drain. Okay, that's what it is. Whereas you can sense the motion of the electrons using the current through one of these channels. So in this experiment, only one of this gate was energized. So you have only a quantum dot. Though the design actually will tell you that you can have another set of dots here, but in this experiment, only one of this gate is energized to have the quantum point contact formed. Okay. So this is the charge stability diagram, the honeycomb diagram, which we have went through in detail. And this is the conductance of the quantum point contact. In this case, is the GLS, the left side sensor, as a function of the same gate voltages. And you can see that the honeycomb diagram, what you get from the direct measurement of the current through the dot, matches exactly with the detector current, where you can see that the current levels, the conductance changes as the charge configuration is changing. This is another example where you have a double quantum dot, and finally you empty the dot and you get to a 0-0 regime. 0 on the right dot, 0 on the left dot. Okay, and here is the gate layout for it, and you have a conducting channel GS2. Okay, and that is what they have used in this experiment. Okay, and you have a double dot here, one dot here, one dot here. Okay, and this is the last few electron configuration of the double dot, the direct current measurement, where you can get peaks only at the triple points, the point where three charge configuration matches. They are degenerate. But whereas this same set of information, same data you can obtain by using the charge sensing technique, by measuring the conductance of the channel here. And you can see that whatever the data that is obtained from the direct current measurement is visible in the charge sensing data also. But that is not the complete story. But you can see here, when you measure the current, you get the information only at these two charge degeneracy points. But you can see the charge sensing technique gives you a lot more information, like how curvy these lines are. All those have meanings. Okay, and when what is the real you know gate voltage, what are the real gate voltage values where this charge interdot tunneling happens, because the current happens only at this point, but the charge configuration changes in all these points. Okay, for example, here 0 0 and 0 1 are degenerate along this line. Along this line 1 0 and 0 0 are degenerate. Okay, whereas along this line 1 1 and 1 0 are degenerate. Along here 0 1 and 1 1 are degenerate. So all this information are have been captured by the charge sensor, whereas the current sensing tells only the information at these 2 points. Okay, so this charge sensor is sensitive not only to change here, it actually can sense the change in the electron configuration of the upper dot also. Here this lower dot which is close to charge sensor, but you can see this sensor is able to sense the change in configuration, charge configuration of any of these dots, both of these dots. And it actually is telling you a lot more information than the direct current measurement to the system. So charge sensor in this way is a lot more superior to the current measuring technique whenever it comes to nanoscale devices where the current levels are really, really low. Okay. Now, let us discuss a little bit the temporal regarding how fast these instruments, these sensor can work, or how much temporal information you can get from these measurements. Okay. So generally what you have is you have a quantum dot device when you are measuring the current through the sensor, that is a channel, and you will get a bump like structure when you measure the current, or peaks in the conductance, and that is going to tell you as this is as a function of the one of the gate voltages, and that's going to tell you when the charge transfer is going to happen. For example, in this case, this is the conductance, and on this side of the gate voltage, you can say that the electron is inside, whereas on this side of this gate voltage, you can say the electron is outside. So here the electron is inside, you have n plus 1 electron. Here the electron is outside, you have n minus 1 n electron. Okay, and at this point, at this gate voltage, what we are saying is the electron, these two states are actually degenerate, or these tunneling process happen. But now this is a voltage sweep. You are sweeping the voltage on one of these gates. Yes, for example, in this case, this gate Vm. All it's telling you that beyond this value, the electron is outside. Above this value, the electron is inside. But it's not giving you much of temporal information for how long the electron took to tunnel out of the dot, how long it has stayed inside the dot. Okay, all these informations are kept under the rug. So, what you would like to have, other than the average charge configuration, average charge occupation, the temporal information also. The temporal information has a lot of importance, especially when your transport mechanism is correlated. Okay. You are also interested in the lifetimes, and all the other aspects of this electron states, which none of these are available when you do this measurement. So, of course, again, there are limitations how fast you can actually get this, do this measurement. Okay, those are decided by the RC time constant of the measurement circuit. So let us discuss the limitations here. Okay. In this specific case, instead of measuring the voltage as a function of the gate voltage. Let us configure or park the device in this configuration where the level inside the dot and the Fermi level are in resonant. What that means, electron can actually tunnel in or out at will. That is driven by the thermal energy available. Okay, that's a fluctuating charge motion back and forth between the dot and the reservoir. So, and I'm going to measure the current through this device, the sensor, versus time. That's what I'm going to do. Okay. Now, we know that whenever the electron is inside, there is small reduction in the current because of an effective negative potential. And whenever the electron is outside, there is an increase in the current. Okay. This region is like, this is your general background of the QPC. The slope is an artifact of the measurement. Okay. Because when you sweep the gate voltage Vm, that also affects the conductance of the channel. So overall effect of the direct capacitive effect of the Vm sweep, the change in this gate voltage, is to reduce the current through the sensor. But the electron tunneling event is going to show up on top of that reduction. Okay. So until this slope, overall slope, is as shown here, is the effect of the direct coupling of the gate to the QPC channel. And this small bump is actually a reduction in the current. Okay, if you look at, you have a reduction in the current here. Okay, this space. Okay, that reduction in the current is because of the electron tunneling event. So when the electron is inside, the current is lower. Electron is outside, the current is higher. Okay, that is why it's important to, or it's interesting to look at the derivative of this curve rather than the bump. Derivative will give you a clear picture, which will give you a peak. Okay, anyway, the point here is you have a, if you stay at this point and if you watch the current, you have a higher current level when the electron is outside, as shown here, and you have a lower current level when the electron is inside. And this is the real data where you can see that a two-stage signal, ups and downs only, which represents the tunneling events of the electron between the dot and the reservoir, which is in a random manner. It's a random telegraphic signal because this is driven by the thermal fluctuations, okay, thermal energy. So whenever the current is high, the electron is outside, and the lower level shows the electron is inside. So the width of the highs tells you how long the electron was out. The width of the lower level is going to tell you how long the electron was inside. Okay, so you are directly accessing the temporal information and also spatial information. So you are getting both here. The spatial information is telling you it's telling you whether the electron is inside or outside. The temporal information, by looking at these durations, is telling you how long it has stayed outside, how long this electron have stayed inside. And it's also telling you the tunnel rates too, actually. Okay. Now, the question is, what is the limitation here? Limitation is the measurement circuit. So you have the quantum point contact, which is a high impedance device. Okay. Then you have a lot of wiring of this measuring equipment, which will add you some capacitance. So the this impedance plus the capacitance of the circuit is going to give you a bandwidth of the measurement circuit. Mostly it is the RC time constant of the circuit. RC time constant of the circuit. Now, on top of that, you also have the bandwidth of the amplifier, preamplifier, this amplifier here, that is telling you how fast you can measure. For example, in this specific case, it was like 1 millisecond time constant. That is for 1 kilohertz. Okay, that is the amplifier setting. Okay, or filter setting in the amplifier that was used for this measurement. So on not only the filter setting, but also the RC time constant circuit, which also will fall eventually in the similar ballpark, in the similar regime. You can think that these quantum point contacts in this measurement regime are like 100 kilo ohms in that range. Okay, and you can assume that the wire has nanofarads of capacitance. Okay, so when you match all these things, you will see it's again a few tens of kilohertz maximum. That is the fastest you can measure by this technique. Okay, and in one of the coming lectures, we will actually revisit this point again, and we will go through a revolutionary technology. How can you measure this charge motion, this dynamics, much faster time scale using a slightly different technique? Okay, that we will discuss in the next lecture. So, in nutshell, what we are what we learned is the quantum point contacts are ultra-sensitive mesoscopic charge sensors. Actually can sense the motion of one electron in a solid state circuit. And you can also get not only the spatial information but also temporal information. You can also get information when there is no current flowing through. It doesn't require a flow of current. All it's going to sense is the motion of the charge or the change in the charge configuration. Okay.